take a look at a modern combined cycle gas turbine. Right now, manufacturing capacity for these massive machines is booked out for the rest of the decade. The reason for that demand comes down to raw efficiency. In the energy sector, squeezing out just one extra point of efficiency from a turbine yields up to $25 million in lifetime fuel savings. To hit those efficiency numbers, you have to run the combustor hotter before the gas hits the blades. Modern inlet temperatures reach 1600 degrees Celsius. That is hotter than most lavas, and well beyond the melting point of standard steel. And it is not just the heat. The blades positioned directly after the combustor rotate at around 12,000 revolutions per minute. That rotation generates an outward centrifugal pull of about 20 tons per square inch. Expose normal metal to extreme heat and rotational stress, and it stretches over time. Engineers call this creep. Eventually, the metal elongates, scrapes the outer casing, and fractures. This leaves engine designers with a severe physics problem. They must construct a machine part forced to operate in an environment mathematically guaranteed to melt and destroy it. The first line of defense is abandoning steel entirely. Instead, the industry relies on superalloys based on nickel, a metal that has a naturally high melting point and retains its strength under intense heat. To stop creep, we address the atomic structure. Metals are stacked planes of atoms that slip past one another under force. To lock them down, metallurgists add aluminum and titanium, creating gamma prime precipitates. These clusters wedge into the gaps, halting the slip. There is a catch. Aluminum and titanium react instantly with atmospheric oxygen. To create these superalloys without ruining them, engineers had to figure out how to melt and cast the metals inside a complete vacuum. Chemistry successfully fortified the metal against standard creep, but as power plants demanded even hotter inlet temperatures, a deeper structural vulnerability in the metal emerged. Liquid metal cools into randomly oriented crystals. The jagged spaces between them, called grain boundaries, tear apart under stress. To fix this, directional solidification uses a bottom chill plate to freeze the metal upwards, growing vertical columns that eliminate the weak seams. This directional solidification provided the precise structural strength required to build the engines for the SR-71 Blackbird. To eliminate boundaries entirely, researchers added a smoothly curving helix shape, a pigtail, above the chill plate. As vertical crystals grow, the pigtail acts as a filter. Only one winning crystal navigates the turns, expanding to fill the entire mold, creating one solid, continuous crystal blade. But even after achieving a flawless internal lattice, a raw, simple crystal blade will still melt if you drop it into a modern combustor. Current combined cycle gas turbines operate at 1600 degrees Celsius. At that heat, raw metals simply cannot survive. Engineers apply a multi-layered ceramic thermal barrier coating to repel heat. Then, hollow core passageways route cooler compressor air out through laser-drilled surface holes, creating a flowing film of air that physically pushes the 1600-degree gas away from the blade. Getting a piece of metal to survive hell requires an exhaustively layered defense, with precise chemistry, flawless structural growth, and constant active cooling. We have pushed nickel-based superalloys to their absolute thermodynamic limit. To squeeze out any more efficiency, the aerospace industry is pivoting away from traditional metal. It starts before manufacturing even begins. Companies now build digital twins of turbine blades, using artificial intelligence to run thousands of virtual hours of thermal and mechanical stress tests before a single drop of material is ever poured. When it is time to build, traditional casting is being replaced by additive manufacturing. High-precision 3D printing allows designers to map out microscopic internal cooling channels that were physically impossible to construct before. But the true successor to the superalloy is a completely different material class, Ceramic Matrix Composites, or CMCs. By embedding rigid ceramic fibers within a surrounding ceramic matrix, engineers have solved the brittle fragility of standard ceramics through a mechanism called crack deflection. These composites offer a massive dual advantage. They can operate hundreds of degrees higher than the limit of nickel, requiring far less cooling air. And because they possess about 1/3 the density of superalloys, the weight reduction translates into immediate fuel savings. The pressure driving this innovation is constant. The urgency to extract more power from less fuel accelerated sharply during the oil crises of the 1970s, and it dictates the industry today. The modern turbine blade is what happens when we refuse to accept physical limits. We have manipulated atoms, eliminated crystal boundaries, and printed impossible internal geometries, all to keep a single piece of material surviving inside a continuous fire, just to keep the lights on.